So quantum numbers is definitely an intimidating topic to talk about. I do have some experience, not a lot, so if I say something incorrect in here, feel free to comment, let me know. But I want to go through and try and translate what these are and what they mean. Now, a quantum number is something that comes in quantum mechanics where you have a wave function that describes your electron. And that's not something that we use in regular physics. So in regular physics, we would throw something, we could tell what its velocity is based on our initial conditions, things like that. In quantum mechanics, this is our tool to be able to kind of come up with information. And we don't know what these wave functions are for the majority of things. There are a few that we can come up with. But what you can do with those is you can take those and do an operation on them that will give back some information about the electron. So there's some kind of math function I can do on this particular, the wave function that describes my electron here, that will give me back a number that will be information. And this is a famous one, this is a Hamiltonian, it tells you what the energy is. So there is a long math expression here, a long math expression here, and you get back a number in that math expression. And that number is how much energy that electron has. Okay? So that's what a quantum number is, that's what it derives from. There are several different quantum numbers. In chemistry, we typically look at 4. So the first one is n, your principal quantum number, and that is what your energy level is. So if n is 2, you're in the second energy level. If n is 4, you're in the fourth energy level. Okay. For perspective on what that means how far you are away from the nucleus. It's the energy, it's the step you are away from the nucleus. And so the further away you are, the higher the energy level you are. And they get progressively closer as you go on. Now, most people have a concept, an idea, a conceptualization of energy level. The rest of them become very tricky. L is your angular momentum number. And so L is, if we have our nucleus here and here's our electron, L is an angular momentum. And if you think of momentum as kind of how fast you're going and your mass, and a combination of those two, angular momentum is momentum combined with spinning. And so this is how fast we're going based on both the speed and the radial motion. Okay, so how fast we're turning around an object. And that is quantized, okay? So you can have an angular momentum of 0 or 1 or 2 or 3, and that will lead to different things. In particular, in this case, L equals 0 will produce an s orbital. So the probability distribution of something with an angular momentum of 0 is spherical. Whereas for an angular momentum of 1, it's no longer spherical, it's now lobe-shaped, and it can be in different directions. For L equals 2, who even knows what that is anymore? Okay, so this is a quantum number that kind of describes how the electron is moving around in a circle, and then M takes that and makes that even more specific. It adds directionality to it. Am I moving this way in a circle, or a loop, or circular pattern? Am I moving this way? Am I moving that way? So this will distinguish between sets of orbitals, and this is really easy to tell in the lab because you can apply a magnetic field in a certain direction, and it will differentiate those quantum numbers. So we tend to resort this to which orbital am I in of all the potentials. And the last one is spin. Spin is an intrinsic spin, and it's basically the rotation of the electron itself. And there are 2 possible angular momentums for an electron, +1/2 and -1/2. And those in the higher level physics become very, very interesting. So that's what those are. Now how do you go about communicating them to people? Well, there are a few different ways. So when you were doing electron configurations in chemistry, and you were writing things like this, you're communicating a bunch of quantum numbers. The 1 here, the 2 here, and the 2 here, those are n values. So if I take a look at these 2 electrons here, this is n equals 1, and L is 0, because it's an s orbital, and M is 0. We don't have any options on that. And your spins for these, one is +1/2, the other is -1/2. Okay, so there's information embedded in an electron configuration that tells you what the different quantum numbers are. Whereas when I look at 2p3, for example, now I've got some different things. Now my n is 2. So I have a different quantum number for those 3 electrons. The L is 1. S orbitals are L is 0, p orbitals L is 1, d orbitals L is 2. The m values for these will be different. One will be -1, one will be 0, and one will be +1. Okay, so now I have electrons that have angular momentums that are distributed differently in space. The directionality of their motion around the nucleus. The spins for these will all be the same. They would either be +1/2 or -1/2. So there's some information you can derive from electron configurations. However, there do tend to be choices that you still have the option of making. So a lot of times, instead of starting with electron configurations, you'll actually start with what are called orbital diagrams. Now, an orbital diagram will just have a series of lines. So first and foremost, the number of lines will give you information as to what orbital it is. And a lot of people miss that, and then that builds and they don't understand anything. If you have 3 lines, you have a set of p orbitals. If you have 5 lines, it's a set of d orbitals. 1 is s, 7 is f. That's it. Once you're getting into weird g orbitals in theory, you're going to be dealing with one of those situations. So when you see 3 lines, you want to think, okay, it's a set of p orbitals. So let's say that I'm in the 4th energy level, and I have a set of p orbitals, and I draw an electron like this, and an electron like that. And I say, what are the quantum numbers? Well, obviously n equals 4, because I said so. L for these is going to be 1 for each. Okay. M, I have options. So one of these orbitals is -1, one is 0, and one is +1. Which one is which is really arbitrary because I can rotate my directionality of my perspective. Usually you'll see them written like this in order. They don't have to be there. Well, let's stick with them in order for now to keep it simple. This one will be a -1m, and this one will be a +1. And then again, the spin usually indicate by the direction of the arrow. Spin up is an arrow pointing up, spin down an arrow pointing down. These could easily be flip-flopped, but they will both be the same at this particular juncture. So an orbital diagram is great at giving out information for quantum numbers. It's quick to derive from. There's a lot of visual components to it. Okay. The other thing you can do, you could just tell them. So we could go through and say, oh, I have 2 electrons. Here are their quantum numbers. This one and the other one has n equal to 4, L equal to 2, m equal to 0, and s equal to +1/2. And there you go, there's your set of quantum numbers. The interpretation is I'm in the 4th energy level, I'm in a d orbital. I have 1 electron in one orbital, 1 electron in another orbital state, and the spins are both in the same direction up. So if I were to draw my set of d orbitals, there's an electron and there's an electron. There could be others, but I haven't discussed them here. So there's different ways to communicate those. The other way that you really could do is you could also just draw an orbital. If I tell you this is a 1s, and here's a 2s, then I've got n equals 1, L equals 0, m equals 0, n equals 2, L equals 0, m equals 0. Once you have your quantum numbers, what do you do with that? Well, there are weird rules in physics, for quantum physics, that we try and start teaching in regular chemistry. And they might not make a ton of sense at the beginning because they're not things that kind of correlate with rules you see in regular physics. There are 3 that come up in regular chemistry, and that at this level now you should be able to explain a little better. One is the aufbau principle, one is Hund's rule, and the other is the Pauli exclusion principle. Okay, and those are named after famous scientists. Aufbau is really simple. It's actually just that electrons will go into the lowest energy state available to them. So they go into the 1s state first, and then the 2s, and then the 2p, and then the 3s. There are, of course, some huge discrepancies with that when you get into the transition metals, because 3d is slightly below 4s in a purest sense, but when they become occupied, that tends to fluctuate. So a lot of electrons will move to the 4s after being in the 3d, and that gives us all kinds of weird configurations. Silver is 3d. Silver is 5s1, 4010, which goes against kind of the order we have on the periodic table. Exceptions to the aufbau principle. So if I have a 1s and a 2s orbital that's unoccupied, then an exception to the aufbau would be if this went into an excited state and that electron hopped up. So during light emission and light absorption, you're going to see violations to the aufbau principle. If you have an electron configuration written out in the wrong order, that would be an exception to the aufbau principle. Hund is when you have a set of orbitals and you start to fill them, that when you go in to put in a new electron, that there is a repulsion that's greater when the electron is put by these two. So if it's put in the same kind of area as them, there's a greater repulsion. So if you're going to put a third electron in, you would put it in an unoccupied state first before putting it into the others. Okay, and that's simply just due to regular old electrons repel electrons, and then they would be in a closer vicinity to them. Pauli exclusion principle says you can't have the same set of quantum numbers for two electrons. And that has all kinds of really cool implications for why metals are what they are. And in chemistry, we often simplify that down to chemistry examples by saying you can't have two electrons in the same orbital state that have the same spin. Or you can't have more than two electrons in an orbital. But any set of four quantum numbers where they would all be the same would violate this principle. And so if you had this, then that would violate the Pauli exclusion principle, and that would be no good. Okay. So from there, then we want you to go through and be able to analyze situations where we give a set of quantum numbers, and we say, okay, if n equals 4, and L equals 1, and M equals 0, and S equals plus 1/2 for one electron, and the other one is 4, 1, 0, and minus 1/2, and there are no other electrons. What's wrong with that? And just by looking at those numbers, you can give a violation of one of the three previous rules. The easiest thing to do with this usually is to draw it out. We're talking about a p orbital, and we have this. So drawing that out, that's clearly a violation of Hund's rule. One of those electrons should have gone into a separate orbital state. Okay. And then the last couple things that you can do with quantum numbers, one is that you can describe relationships between just simple things. Like for example, if you know the energy level n, and you square that amount and multiply by 2, that'll be equal to how many electrons there are in a given energy level. So in the third energy level, you have 3 squared, 9 times 2, 18. There are 18 electrons that can occupy a state in that third energy level. In the fourth energy level, it's 32. In the fifth, it's 50. And so on and so forth. If you know your n value, then you know your L value will be somewhere between 0 up to n minus 1. So the first energy level, you can have L equals 0. S orbitals only. In the n equals second energy level, you can have 0 or 1, S or P. Third energy level, you can have 0 to 2, S, P, or D. Fourth energy level, now we add the F. At fifth energy level, technically you add the G. Although we don't have any electrons occupying that in their ground state for a current element. In addition to that, once you know your L value, so L equals 1, L equals 2, then your M is going to range from negative L to positive L. Okay, so for an s orbital, M can only be 0. L equals 0, there we go. For a p set of orbitals, it can be negative 1, 0, or positive 1. For a d set of orbitals, it can be 0, negative 1, negative 2, positive 1, or positive 2. For f orbitals, it can be negative 3 all the way up to plus 3. So there are relationships between these numbers that we want you to be able to kind of rationalize and work with and become familiar with when we're doing this. Now, what a quantum number is very abstract, it's very mathematical, but it is also real. It's a way of describing the electron that would be like saying, what's the speed of something? And it's how we would work with them. So we're trying to introduce you to that concept so that if you go on later, that you have kind of a fundamental set to kind of be able to work within such an odd scheme of things. Okay? And there are interesting things that arise from this. If you look at magnetism, which deals with paired and unpaired electrons, for paramagnetic, diamagnetic, that's something that's well described using quantum numbers and orbital diagrams. Okay? So that's the basic overview of what these are, but just going through and working some out and taking some practice will really help kind of solidify that understanding.